cloud. Just starting the recording now. Sorry if you're joining us late. What we've done is we've introduced the equations of motion for a rotating planet, and we're just beginning to solve those numerically. Okay, so continuing on here, what we have is an RK4 stepper. That is a sequence of steps that can be used to solve any right-hand side. In this particular problem, the right-hand side we want to solve is the right-hand side of the equations of motion. We have to code these up as a function. So here is my function. It's a function that takes a general state vector. In my case, I'm defining my state to be the position x, the position y, vx, vy as the state. There's really only one parameter of significance here, and that's the product of g and m. I could pass g and m separately. I just decided to pass them as a product all pre-multiplied. It's just this constant. This is basically saying how strong the force of gravity is acting on this thing. It's right, that's all the way through. R, the distance between the two particles, the distance between the Earth and the sun, itself isn't a variable that's external. It can be calculated from x and y. So we do that within this function. We calculate explicitly R is the square root of x squared plus y squared. And then what we need to do is pass back or return the derivatives of x, derivatives of y, derivative of vx, and derivative of vy. And according to the equations of motion, those are vx, vy, and then the two terms given below. So this is what the right-hand side needs to do. This function could be called anything you like. It could be called right-hand side. It could be called my function. I'm calling it F planet because it's the forces to do with the planet. So let's do that. We need some application that we're going to run and evaluate what the system is going to be. So here is my driver program, a master program that's going to run this whole thing. We have a bunch of parameters we could pass in. So just as a default, a set of defaults, let's just choose the Earth. You can go off to Wikipedia, you can go off to Google, go off to your favorite textbook, and you'll learn that the Earth is a distance away from the sun on average of about 150 billion meters. So 150 million kilometers away. We're in the XY plane. There's no direction north, south, east, or west when we're thinking about the orbits. So let's just take, with complete generality, we're going to start at the maximum x position and start on the y-axis, or y is equal to 0. Did we have to do that? No, but we can start anywhere we like. If we're starting on the y-axis, we want to be moving in a direction at right angles to the vector between the mass of the Earth and the mass of the sun. So I want to have the velocity in the direction of x being 0. And I want to have the velocity in the direction of y being whatever speed I need to make it all the way around its orbit in one day, in 1 year. Okay, if you imagine a circle, you can figure out the circumference of the circle is if you know its radius. 2 times pi times r, that's the circumference of the circle. As a default, as an initial variable, how fast should the planet Earth be traveling? Well, it should be traveling fast enough so that it covers its entire circumference, 2 pi r, in 1 calendar year. 60 seconds per minute, 60 minutes per hour, 24 hours in a day, 365 days in a year. If you wanted to make it 365.24, as in account for the leap year, you're more than welcome to. This is just a sane, reasonable default, something in meters per second. That's approximately how fast the planet Earth has to be traveling. We're going to run this model for at least a year so we can see it going all the way around the sun. So let's run it for 60 times 24 times 365. You'll notice that I left those all as terms that have been not multiplied out because there's no need to multiply them out. The computer can do it for me just fine, and it makes it clear where I'm getting the number from. It's something like 10 million seconds is what 1 year is. And then for a time step, I'm just going to choose a day. Splits the year up into 365 pieces. So I'm going to predict the location of the Earth as a function of time. In terms of the structure of the application, you set up a state vector, x, y, vx, vy. You define whatever parameters or constants you need. I only have one, the product of G times M. I'm going to create a list of all my parameters. There's only one of them. And then I take that parameter list and the state vector and the function, and I pass that all into the stepper routine. That's something that I can iterate through. This is really just an iterator, and it gives me back all the results. So here we go, right? So that's the structure and the path we've been seeing all the way through. So if I run this program, what you're seeing is in seconds, so 0 time is where it starts. After 1 day, 86,000 seconds, it has moved from this position to this position. So every day you are moving 2 billion meters. So it's pretty good. We're moving at a really good clip. You can see that. Here's the velocity. This is in meters per second, right? We are moving at 29,000 meters per second, right? 29 kilometers every single second is how fast we're going as a planet. And this thing will run for 365 steps until it gets to the end of the time. We don't really want to look at the data just as a table. We want to look at it as some sort of visualization, a plot. So let me write a function that plots this kind of data. Well, here we go. I'm going to be a little bit more creative with this plot. It's going to take the data in, and it's going to plot a dotted line. And then to emphasize where the origin is, I'm going to put at point 0, 0, a dot that's yellow and pretty big. It's the sun. I'm going to draw the sun. The Earth, what I'm going to do is plot it not only as its trajectory, but also where it ends up. So I'll go to the very last value in this table and plot a dot, and I'll make it black, and it'll be smaller. And if you wanted to make it blue, be my guest, you could. This is a function that will sort of show you a schematic of what the orbit looks like, so that when I call it planet plot of data, I get a picture like the following. So there we go. This is how this thing works all the way along. There's the sun, there's the Earth. The sizes are completely arbitrary. This is not to scale. The sun is not this big. The Earth is not that big. They're not that close relative to their sizes all the way through. How did you get it to say, there's a question in the chat, how did I get it to say 1e to the 11 in the corners? So the initial data, you see this number right here? If it tried to actually print out 1.4960 or 14960000000, this would make this very cluttered. So what the graphing library does automatically is if you're printing out numbers that are very large, such that they can't fit in a certain number of characters, it converts it to scientific notation and then just puts this number up here. So this is 1.5 times 10 to the 11, 0 times 10 to the 11, minus 1.5 times 10 to the 11. It's a default of matplotlib. I'm pretty sure I can get rid of it. Yeah, there we go. Can you get rid of it so the number is in the label instead? Yes, you can. I would have to look that up for you. But you definitely can get rid of it if you wanted the full number in its glory all the way on the left. Okay, so that's just a way of saying, and there we go. It's tracing out a circular orbit, and a circle is a kind of ellipse, so that sort of makes sense. What we have shown is the force of gravity acting towards a planet does cause it to go around in a circle, which should not be that surprising. But the point is the force of gravity as written down, starting from this system of equations, what you get back as the solution is an orbit, a circular orbit, if you have it going around at a fixed speed all the time. Okay, so that's the setup. Okay, orbits are not always circular. They also can be elliptic. I've used as a default the average radius of the Earth's orbit and chosen the initial velocity to be the velocity needed to complete one orbit in one calendar year. If instead we were to start the orbit of the planet a bit further away from the sun, so if initially we're talking about 150 billion meters, let's start a planet at 200 billion meters away, a little bit further away, same initial speed, and run it for 1 year. And what you're going to see is the and same initial starting spot, but it ends up going further away from the sun. It doesn't trace out a circle. It traces out this sort of shape. It stops here because we're only simulating this for 1 calendar year. If I start my planet not here, but closer, at say 100 billion meters away from the sun, and I run the same simulation, what you see is the Earth that started here, the planet, which is started in 1 times 10 to the 11 or 100 times 10 to the 9, has gone all the way around, and then goes all the way around again, and it stops right here. So there's a couple observations. Depending on the initial position, and it turns out the initial velocity, you can change the shape of the orbit. It's only going to be a circle when it has a very special initial starting distance and starting speed. And the other thing is the periods are dependent upon the motion. The same planet, same mass, same sun, depending on how far away you are, that sets what your period's going to be. If you're farther away, you need to go more than a calendar year. If you're closer, you have to go less than a calendar year all the way through. Okay, so let's just play with this for a second. Let's modify Tmax and try and figure out what the actual period of these things are, right? So if we go to the first one, we know that we need to go further all the way around. You could use widgets, you could do a plot, or we could just go simple and say, what happens if it was 2 years? Okay, I've gone all the way around. Okay, maybe it's 3 calendar years that I have to do. Nope, I can't seem to type. Oh, that's a little bit too far. 2.8. A bit further, 2.85. Looks pretty, 2.86 maybe. There you go. So to get one orbit, 1 year, if you happen to be a distance of 200 million meters away, you basically have an orbit of 2.86 years. Likewise, when you're closer, your orbit's going to be smaller. You don't need to go to a full year. You can do less than a year. Let's change it to a half. Oh, a half's too much. Let's go to 0.2. 0.2 is too little. Let's go to 0.3. A bit further than that, 3.5. Oh, we're getting there, 3.6. Oh, there we go. Okay, so depending on how close you are to your planet, even though this is a bit weird, this one is the one that's far away. This is the one that's starting closer. Okay, so look at the scale. Do you see the 2 here? This simulation has it starting further away than the Earth. This one has it starting closer than the Earth. They start with the same velocity though. So this is traveling relatively slow for its orbit. This is traveling relatively fast for its orbit, which is why it has this asymmetric sort of feel. This idea of tracing out a circle, which is not a circle, it's an ellipse, and the sun being where it is, this is Kepler's first law. Orbits of planets are ellipses where the sun is at one of the 2 foci. And it could either be the near foci or the far foci. It could be either one. Both are allowed under Kepler's law. It depends what the relationship is between the initial position and the initial velocity. Okay. If you want to have a circular orbit, so something that you're going to require v square, it to be a perfect circle and not an ellipse, what we want to do is we need to think about how the acceleration and the speed, v, relate to each other. If you remember back from Physics 1050, we talked about circular motion. The acceleration for circular motion is equal to v squared over r. That's going to be the acceleration that's always directed towards the center in a gravitational force. If you have a circular orbit, then the acceleration is going to be v squared over r. So its force is going to be mass times v squared over r. And that's going to be equal to g times m divided by r squared. We can solve this system. We can solve the system for v and have v is equal to the square root of gm divided by r. That's the condition for when the speed and the radius are set in such a way that you're going to get a circular orbit. I set the speed in the first example This is a situation that satisfies this condition. This is a situation where the speed and the radius are chosen so that this is true. V is proportional to 1 over r squared. In these two examples, V and R are chosen to not satisfy that relationship. It is no longer true that V is going to be equal to this. This is a condition about circular orbits. If the orbit is circular, then we can figure out its period by just saying 2 times pi divided by r, the circumference, divided by the speed. So what's going on here is in circular orbits, the speed is a constant. In elliptical orbits, speed is not a constant. So that's a fundamental difference between the two things. But if you have a circular orbit, then you can fairly quickly figure out that 2 pi r divided by v, that's going to be the period of this orbit. Well, if you take that period and relate that back to this expression right here, so take this expression, take v equals stuff, take the v, substitute it into here, so we get rid of the v, square both sides, you're going to get a relationship between the period and the radius. That's for a circular orbit. But of course, this is just a special case of what Kepler's third law says. Kepler's third law says that if you take the ratio of t squared and the semi-major axis cubed, which for a circle, the semi-major axis A and R are exactly the same thing, then t squared over a cubed is equal to some number. That some number is a constant, and that's what Kepler's third law says. It says if you take the period of any orbit and its semi-major axis cubed, come up with that ratio, then you're going to get some constant number for all the orbiting bodies in the system. So we've just derived a special case of Kepler's law. Okay. Right. So what we can do now is we can sort of test Kepler's law, not just for this case where the velocity is a constant, but we can calculate and test Kepler's law for the 3 example orbits. So we have 3 orbits here, right? The first orbit is it's going around in a circle. I've saved the data in a variable called data. I've got my second orbit here where I've got an orbit. This is the one that's starting far away, relatively speaking, from the sun. That means it actually ends up going even further on the far side. This is saved in a variable called data far. And then the third one, this is data near. It's near in the sense that it starts up nearer than the Earth does. And when it starts with the same speed as the Earth, it actually ends up going even closer to it all the way through. So those are my 3 data sets. So what I can do is I can calculate the semi-major axis, the period, and then what that number is. So this is, I think, straightforward, but I want to make sure it's sort of clear what I'm doing. The semi-major axis is the distance between along the largest diameter or axis of an ellipse to the center of the ellipse. So what it is you take the circle, you take this distance right here, you cut it in 2, and then whatever this distance is remaining, that's your semi-major axis. For a circle, the semi-major axis and a radius are exactly the same thing. For a ellipse, what we're considering here is you take the semi-major axis, you cut it in half, and this quantity right here is what we call the semi-major axis. So what I'm doing to figure it out is I take the largest value of x, this is x dot max, I take the smallest value of x, x dot min. These are methods that work on these arrays, basically picking off the smallest value and the littlest value. Because I've set this up so that the sun is always at the system 0, 0, I know that the maximum is going to be a positive number, the minimum is going to be a negative number. So max minus min gives me the distance across this axis, divided by 2, that's going to give me the semi-major axis. Okay, and that's exactly what I've done. Right. So take the difference between the max and the min, divide by 2. That's going to be your semi-major axis. The first one went for 1 year. So if you go 2 cubed divided by a thing, you get a number. If I do it for the one that started far away and I run it for 2.88 years, I get another number. Is that the number I got? I'm going to go back and check. Maybe it's 2.86. There's a bit of, there. We're going to go with 2.87. And then for this third one, the one that's near, I think we came up with a time, I did it before 3.36, but what did I do this time? Yeah, 0.36. You get another number. Okay, and here's the point. This number, and this number, at least to one, actually 2 significant figures. To 2 significant figures, 3.0 times 10 to the 19, 3.0 times 10 to the 19, 3.0 times 10 to the 19, or minus 19. All 3 of these things are the same value. That's what Kepler's law says, is that ratio is always the same. And these are for non-constant speed. These are not circular orbits. Well, the first one isn't, but the other 2 are not. The speed is changing in time all the way through. And what we can solve for is this value, whatever it is, should have a numerical value equal to 4 pi squared divided by gm. And again, if you use the gravitational constant and the mass of the sun, you're able to figure out that this number. So theory would say it's 2.97. My numerical experiments are coming up with this. Just 2 significant figures. Everybody's agreeing. And of course, I'm not coming up with these any better than 2 significant figures. So I think that's all pretty consistent. What did I want to say? I guess we could just sort of talk briefly about the velocities, just to sort of prove what's going on here. If I take this data dot t, data dot v, well, let's do it this way. V is equal to data dot vx squared, data dot vy squared, square root. And I was to plot d versus v, you're going to get something which is basically a constant. Now, you may look at this thing and be like, that's not a constant, that's varying. But again, look at the numbers. See the 298? For all intents and purposes, that's just a straight line. Right? On that scale, that's just a straight line. The velocity is effectively a constant all the way through. Alternatively, if I look at the one that's starts off near, whoa, can you see how that particular one, I got to change my scale. I really got to change my scale. There we go. So now, rather than varying just by a few kilometers per meters per second, it varies by like almost an order of a factor of 2. So as this thing moves around the sun, its speed is no longer constant by any means. It's slow here and really speeds up to twice its speed and then slows down again and speeds up again. The speed is no longer a constant all the way through. Nonetheless, even though we haven't calculated the speed, if we just look at the period divided by this major, it's a constant in all these cases. So this is sort of what Kepler's law is saying. It's saying something more than just circular motion. It's saying that the ratio of the total period, the semi-major axis with these 2 axes is going to have a constant relationship. Okay. Up to now, we've been dealing with some pretty big and pretty small numbers. The comment was made in the chat that in the original distances, we were dealing with numbers like 10 to the power of 11. These constants that we're calculating are 10 to the minus 19. I'm having to deal with times, which are in the tens of millions of seconds. I'm dealing with 10 to the 30s and 10 to the minus 11s. We're jumping around numerical orders of magnitude all over the place. Turns out that for these kind of astronomical problems, there's a better set of units. You could do something more. You can do something if you just choose better units. You're familiar with systems of units. So the SI system of units, meters, seconds, kilograms, those will give you unwieldy numbers. They're totally fine. They're just hard to wrap your mind around. It turns out to be convenient to choose a new system of units for which the magnitude of the product G times M is not a giant number and not a tiny number. So right now, G times M is a tiny number, right? It's 3 times 10 to the minus 19. We can choose G times M to be a different number, and that just changes the units, basically the units for distance, the units for time, and hence the units for mass all the way through. For our solar system and the planets that are in it, it's convenient to choose as our base unit of length the distance from the Earth to the Sun on its semi-major axis. That is, if you look at where the Earth is relative to the Sun and define that to be a standard unit of measure, that's called 1 astronomical unit. And it's defined to be 150 billion meters. So 1.496 times 10 to the 11 meters. Let's define that as a new unit. It's called an astronomical unit. When you deal with astronomical units, rather than dealing with 60 times 60 times 24 times 365, which is about 3 times 10 to the 7 seconds, let's define a unit of time to be 1 Earth calendar year. So the units are going to be, time is going to be measured in years, and distance is going to be measured in astronomical units, or 1 AUs. What that means is you're able to convert things from meters and seconds into years and astronomical units. And so this expression, 4 pi a cubed divided by t squared, if a is in units of astronomical units and t is in units of years, for the Earth, a is equal to 1, t is equal to 1, that means that GM has the units of 4 pi squared. And that's it. Its unit is 4 pi squared, or its number is 4 pi squared. So something around the order of 12-ish, 13, 14, a nice moderate number. It has odd units. It has units of astronomical units cubed divided by years squared, but those are just the units. And that scales everything in the problem. So in our 2 examples, when I started off with a distance of 200 billion meters away, well, another way of saying that is that's just 1 1/3 astronomical units. If I start a distance of 100 billion meters away, that's just 2/3 of an astronomical unit. So if we rewrite the problem so we're dealing with astronomical units, we don't need to worry about all of these or 10 times, or times 10 to the power of 11, or times 10 to the power of 19. I would say that rather than trying to change the scale on these things and get this to disappear, if you're getting a lot of e to the power 7, or 10 to the power 7, 10 to the power 11, 10 to the power minus 19, you just haven't chosen an appropriate set of units for your problem. There'll be some way of either non-dimensionalizing it or going to a set of units which are more convenient for what you're dealing with. And this is allowed. You're allowed to not use SI units for everything. I don't necessarily use imperial units, but if there's a better system of units for the physics you're doing at the scale you're doing it, you are empowered and allowed to use those units. You just need to say what they are. You just need to say, from now on, 1 astronomical unit is defined to be equal to 1.496 times 10 to the 11 meters. It just makes the plots and the graphs and the arithmetic so much easier. Okay, let's take some of those astronomical units and take a look at the actual data of the planets in our solar system. So after repeated observations, astronomers and those who measure such things have come up with the following data. This is how I would set it up as a data frame, but you're welcome to look at it in a formatted sort of way. This is the period of the orbit of each of these planets and the semi-major axis of each of these planets. The Earth has units of 1 and 1 because that's how we scaled everything. Mars, Venus, and Mercury are all relatively close to the Sun. They're called the inner planets. And then Jupiter, Saturn, Uranus, and Neptune, they're much further out. Try this again. This column is the distance away, and these are all further out because they're the outer planets. One of the relationships, of course, is when you're near to the sun, you have a small, short year. When you're far away from the sun, you have a larger year. I have to admit, as I was preparing this lecture, this kept on disappearing and appearing and disappearing and appearing. I never know whether or not to include Pluto in the list of planets or not. It's officially not a planet. If you do include Pluto, you really should be including a lot of other things. But I left it in there because I wanted one more dot. But if you want to take it out because you're like, no, Pluto is a dwarf planet, doesn't count, go ahead. Does not change the story. Okay, so here we go. We got some data. Now, I've done something a little bit different in this particular data frame that we haven't seen before. I'm using what's called an index. We have, so I'll just get rid of this, this line for a second, just to show you the difference, because this is a bit new. Normally what we've done is we've created data that have the first row, the second row, the third row, the fourth row, the fifth row. Well, these are labels. These are perfectly good labels for each one of these rows. In the pandas data frame world, this row or these labels are called the index. So what you do is you can take the data set, say, I want to have the column planet be my index, and then that goes away. What that means is if you want to talk about a particular planet, do you remember how we have to use iLock to figure out the last row or the first row? Remember we would do this kind of thing? That's not going to work anymore because that was the index when the numbers were 0, 1, 2, 3, 4, 5, 6. The index now planets. What? What am I doing wrong? Cannot index location with a non-integer key? Of course you can. Oh, sorry. I got you. I was flipping around. Let's try this again. That's label-based searching up. So what you're doing here is you're grabbing the location for that label. Alternatively, and this is where my mind was, I had it right. iLock is the integer representation of the first, second, third, or fourth. So you either could use iLock for the third, fourth, fifth, or sixth, or the label of whatever one you want. This might be more clear because the third planet all the way through. So that's how pandas labeling. This is label-based indexing. This is position-based indexing. Okay, remove the iLock. I figured that problem out. Shouldn't string identify, could you, bunch of people. Okay. Okay. Could you get your index to be on the right side instead of the left? I mean, here? On the right-hand side? I'm sure you could. Just involves printing the table out. That's sort of just the default way of rendering a data frame. You can print out data frames any which way you like by just putting print statements. Internally, this is just a bunch of like HTML. I'm sure you could. It would just require some coding. Can you go through the index explanation again? Right. What I'm getting at is when you've got a data frame and you've got a bunch of things in your data frame, you either can talk about the data frame being indexed just by numbers, as in the first row, the second row, the third row, the fourth row. But the way that Pandas is designed is expecting that index to have meaning. So it includes this idea of setting the index. And what that means is choose one of these columns to be the thing you're going to do lookups on, to look up, like as in an index, what you're looking for. So if I look up on the planets, my index now becomes these things. So I can choose the location of the Mars row, and it will give me back 1.88 and 1.523. Or you could talk about the order in which these things are. Okay, just to point out that that's why there's an iLock and a lock. Let's take this data and not consider the planet at all individually, but just consider them all as a set and plot all of the periods versus all of the semi-major axes and look for a relationship between this data. Okay, so here is my plot. So let's say I was trying to explore the relationship between the period T in years and the semi-major axis A in astronomical units. The data is plotted in dots. I could do an NP poly fit kind of line, and that would be the orange thing, to sort of see, is this a linear relationship? And I think it's pretty obvious to see that the orange line does not fit the data very well. I could also make a plot with a quadratic fit. And if you look at the green line on this larger plot, you might be tempted to say, oh, that's not so bad. That sort of looks a bit quadratic. Maybe it's a quadratic fit. But if I just take these dots right here that correspond to the 4 inner planets and do the exact same plot, so it's the same green line, it's the same blue dots, but I'm just redrawing it where I've zoomed in, you can see that quadratic fit isn't actually fitting the data at all. This technique of having one plot inset from another, that's what I just did is I just wrote a single function that made the plot with its 2 internal fits, and then I just plotted it twice. I plotted it once for the big one, then I made a new little axis. This is an alternative to subplots. If you don't want to use subplots to split your ring up, you can put plots where array axes wherever you like. So in this case, this axis is 1/4 of the distance from the left, 65% of the distance from the bottom, and has the size of 1/3 and 1/3, or 0.3 and 0.3 of the overall figure. So that's its dimensions. And that creates a new axis that I can do another plot of. So I just plotted it again, but changed the limits the second time. You can be creative in your plots. What this plot is showing is the data is definitely not linear. It's not quadratic. And you could do this for cubics and quartics and quintics, and you'd find out that it's none of them. Often, data is not a polynomial relationship, but it's some sort of either exponential or power law relationship. So for many problems, the data is either something of this shape, y is a constant times e to the r times x, or it's a power law relation. Y is equal to a constant times x to the power n. So the difference between these two notations is the x is in the exponent, here the x is in the power. One of these two things. I can figure out what kind of relationship I have by plotting my data on either a semi-log plot or a log-log plot. If you assume it's an exponential form, if you assume your data has this shape, and you take the logarithm of both sides, log of y equals log c plus r times x, you get this expression right here. Plotting this data where you've taken the logarithm of y but left the x by itself should lead you to a straight line where the slope is given by r. So if I do that for my data, and this is where semi-log y comes in, I'm basically saying plot this data and set the scale to be logarithmic just for the y. And you can see that when you plot the data is not forming a straight line. Because the data is not a straight line, we conclude it is not an exponential relationship. Because this curve is not a straight line, we say this is not the right model, so this is not the right idea, we discount it. If you're starting with a power law representation, you can take the logarithm of both sides, log y equals log c plus n times log x. In code, mathematically, you just get this statement. That says that if you were to plot the logarithm, the data on log scales in y and x, you should get a straight line for power law relationships, where the slope is given by the value n. If this is the right relationship, then you're going to get a straight line. So if we do a log-log plot with this data, you should get a straight line. And indeed, for this data set, I do get a perfectly straight line because it is a log-log plot. I can do a polyfit not on the actual data, but on the logarithm of the data. So I'm taking the log of A and the log of T. Remember, log is the natural logarithm. Log base 10. Log 10 is the base 10 logarithm. It's a linear fit in log-log. The components are the slope n and the intercept ln of c, log c. I could calculate the c explicitly. Then I could plot the data a against c times a to the power of n. And because when I use log-log, what that does is it changes the scales to being logarithmic. That function, which is a power law, gets plotted on a log-log graph and goes right through it. And then if I want to be fancy, I could print out the relationship and say that I found that the period is equal to 1 times a to the power of 1.5. That's the power law relationship that the planets map out for their period versus their semi-major axis. And of course, this shouldn't be surprising because this is what Kepler's law tells us. Kepler's law tells us that t squared divided by a cubed has a constant value. If you solve for t, you get t is equal to a constant times a to the 3/2. Well, 3/2 is just 1.5. And in astronomical units, GM is 4 times pi squared. So what you get is t is equal to 1 times a to the 1.5. So there we go. We've proven, we've corroborated Kepler's law. Let's say that all the way through by looking at the data. Last step. We solved this problem with SI units, with meters, seconds, and squares. Let's solve this thing with astronomical units to show you how the code cleans up. If I write it so that my defaults are now x equals 1 astronomical unit, initial speed is 2 times pi, the maximum time is 1 year, this function gets a lot cleaner. GM gets a lot cleaner. The constant is just 4 times pi squared. The code stays the same though. And then I can do my simulation. Now the labels are in terms of astronomical units. So we don't have to worry about any 1 times 10 to the 11th numbers. In astronomical units, now it's 1 and 0 for the Earth. The Earth isn't perfectly circular. It's just very close to being circular. If you want to make something that's non-circular, what you're really doing is you're playing around with the speed. I'll note that I chose an initial velocity of 2 pi. Okay, that might look like a bit of a funny velocity, a velocity of 2 pi, but it's a velocity of 2 pi astronomical units per year. The circumference of a circle with radius 1 astronomical units is 2 pi astronomical units. Divide that by a year, and that's going to be the initial speed. In terms of something that has a slower initial speed or a faster initial speed, it's going to have a different kind of orbit all the way through. Right? So the blue is sort of the Earth-like orbit. Here's one kind of orbit, another kind of orbit. Here in this case, they're all starting at the same location, 1 astronomical unit away from the sun. But depending on the initial speed, they will go into an elliptic orbit, one way or the other. Okay, so all I want to do here is introduce a model with a 2-body problem. What I want to do next week is I'm going to do a 3-body problem, then a 8-body problem, and finish off in the last week with a many-body problem. The particular thing we want to look at is I want to look at some precession of these ellipses. Precession is the idea that this circle right here, this ellipse rather, doesn't have to stay where it is and starts to spin around on its end one way or another. Just in terms of our time, just trying to find something. I'll do this as homework. Yeah, that's what I'll do. There's no assignment for this week. So I remember seeing somewhere think that's the person. You know how I like these podcasts, these various things. Let's see if I can find that. Awesome. Here we go. Okay. So there is a snapshot. I said, I won't make you watch it all the way through. This is relatively recent. It popped up in my feed not too many days ago, and I went, perfect. This is excellent. It's very appropriate to what we're redoing. Mercury has a weird orbit, and this is one of the problems we're going to solve. So sometime between now and next week, if you have a chance to sit down and watch this, I don't know how if you want to make a note or send yourself an email, but this person she goes by the handle of Dr. Becky. She's got a degree from Oxford, does science videos. How does Mercury's orbit and general relativity work together? We're going to talk about that, but I won't show this video in class. So if you had a chance to look at that between now and next week, that would be great. If you want to go do that for 10 minutes right now on your own, that'd be fantastic. Because I think, yeah, I'm not going to do any more on this particular lecture. Okay, is there any questions, comments, things that you'd like to talk about, or are we good today? Nothing. Okay, there's no assignment for you to work on. We have one lab next week to go. One more assignment for next week. We're on the home stretch of this course. Thanks very much. We'll talk to you next week.